How was it possible that Roman engineers built water systems that could withstand catastrophic floods, earthquakes, and centuries of neglect? While our modern infrastructure sometimes fails after a heavy rainstorm, the secret wasn't just in their famous arches. It was in a hidden network of technologies so sophisticated that when archaeologists first discovered them, they couldn't believe these structures were 2,000 years old. Picture this. You're standing in ancient Rome during the height of summer. The city sprawls before you with over 1 million inhabitants, more people than any other city would hold for the next 18 centuries. Yet unlike the disease-ridden medieval cities that would follow, Rome was almost obsessively clean. Public fountains flowed constantly. Bathhouses served hundreds of thousands daily. The streets were washed with running water. All of this in an age we imagine as primitive, without pumps, without electricity, without any of the technology we consider essential for urban water management. The challenge was staggering. Deliver millions of gallons of fresh water daily, across miles of hostile terrain, through valleys and over mountains, maintaining perfect flow without modern materials or tools. The true genius wasn't in the monumental arches you see in pictures. Those were actually just emergency solutions for specific problems. The real brilliance was in what you couldn't see, an invisible philosophy of water that anticipated every possible failure before it happened. Watch this video to the end to discover the hidden technologies buried beneath Roman aqueducts, the mathematical secrets that made water flow uphill without pumps, and the catastrophic design flaw that nearly destroyed Rome's entire water supply, and how one engineer's controversial solution saved millions of lives. What do you think separated Roman engineering from everything that came before it? Was it their materials, their mathematics, or something deeper in how they understood failure? Share your thoughts in the comments, and don't forget to subscribe to our channel for more journeys into the engineering marvels that shaped civilization. I'm about to reveal the best-kept secret of Roman water engineering, something so counterintuitive that when Renaissance engineers rediscovered it, they initially dismissed it as impossible. The Romans built most of their aqueducts underground. That's right. The famous arched bridges you see in photographs represented less than 5% of the total system. The Aqua Claudia, one of Rome's longest aqueducts, stretched for 46 miles. Only 6 miles were above ground. The rest ran through carefully constructed underground channels called spicus, enclosed tunnels precisely engineered to dimensions that would determine the water's behavior for centuries. These weren't simple ditches. Each spicus was a carefully shaped channel, typically about 3 feet wide and 6 feet tall, with a rounded ceiling that served a crucial purpose most people would never notice. An engineer walking through the Aqua Marcia tunnel might pause, examining the ceiling, then say to his apprentice, "Notice the curve. Water cannot pool against a curve. It must run." The rounded design prevented sediment from collecting on top, ensured structural strength against the crushing weight of earth above, and created acoustic properties that allowed maintenance workers to hear changes in water flow from hundreds of feet away. This was the genius of the design. The Romans built their aqueducts to be self-diagnosing. The shape of the tunnel, the grade of the floor, the texture of the walls, everything worked together to make problems announce themselves before they became catastrophic. Workers could hear changes in the water's sound. They could see changes in sediment patterns. They could detect the slightest shift in flow rate by observing watermarks on the carefully smoothed plaster that lined every inch of the channel. But here's where it gets extraordinary. These underground channels had to maintain a perfect gradient across dozens of miles. Too steep, and the water would erode the channel. Too shallow, and sediment would accumulate and block flow. The Romans maintained gradients as gentle as 1 foot of drop per mile, a precision that required surveying technology that wouldn't be matched again until the 18th century. They used an instrument called a chorobates, a 20-foot wooden beam with water channels, to measure level across vast distances. A surveyor might call across a valley to his colleague, "The stones are true. We hold the line." It was this underground network that was the foundation of Roman power. By hiding the aqueducts beneath the earth, they protected them from weather, from enemies, from accidental damage. When barbarian armies besieged Rome, they could cut above-ground sections, but the vast underground network kept flowing. When earthquakes shook the Italian peninsula, the flexible underground channels bent and survived while rigid surface structures collapsed. The underground specus freed Rome from dependence on the Tiber River, allowed the city to grow beyond any previous limits, and made possible the public health infrastructure that kept Roman death rates lower than medieval European cities would see 1,000 years later. Have you ever wondered why Roman cities were so much healthier than the cities that came after them? But what I said before was just the beginning of the story. Are you ready to learn the truth about how Romans made water flow uphill without pumps or engines? Despite images of water flowing downhill through gravity alone, reality was much more sophisticated and much stranger. The Romans understood principles of hydraulic pressure that modern engineers thought were discovered in the Renaissance. The secret weapon was something called an inverted siphon, or siphon invertus in Latin. When an aqueduct had to cross a deep valley, building an arched bridge wasn't always practical. Sometimes the valley was too wide, sometimes too deep, sometimes the terrain was too unstable. The solution was to let the water run downhill into the valley, across the bottom, then use hydraulic pressure to push it back up the other side. Here's how it worked. At the high point before the valley, the aqueduct channel transitioned into a massive header tank called a castellum. From there, the water flowed into huge lead or stone pipes. 9 separate pipes arranged in parallel for the largest siphons. These pipes, each weighing several tons per section, descended into the valley at a steep angle. As the water fell, it built up tremendous pressure. At the bottom of the valley, the pipes turned 90 degrees and ran across level ground, then turned upward again, climbing the opposite slope. The pressure from the descending water pushed the ascending water upward until it reached almost, but not quite, the same height it started from. "We lost 6 feet in the crossing," an engineer might report at the valley bottom, checking his measurements. Within acceptable limits. That small loss of height from friction and turbulence was calculated into the system. The aqueduct on the other side began 6 feet lower than the entry point, and the gradient continued from there. The engineering challenge was immense. The pipes at the valley bottom experienced pressures that could exceed 200 pounds per square inch, enough to rupture poorly made joints or burst inferior materials. The Romans used lead pipes up to 15 millimeters thick, with joints that were welded and then reinforced with iron collars. For the largest siphons, they used stone pressure pipes, carved blocks fitted together so precisely that no mortar was needed, held together purely by the pressure of the water inside pressing outward against the stone. The Pont du Gard in France, one of the most famous Roman aqueducts, is actually just the bridge section of a much larger siphon system. The visible bridge carried water to a header tank from which multiple pressure pipes descended. Most tourists never see the massive stone pipe sections scattered in the valley below, remnants of the true engineering marvel. This was the innovation that made Rome possible. Without inverted siphons, aqueducts could only follow the contours of the land, limiting where cities could be built and how large they could grow. With siphons, engineers could cross any terrain, deliver water anywhere, and maintain the pressure needed for the spectacular fountains and bathhouses that defined Roman urban life. When you walked into the baths of Diocletian and saw water shooting 30 feet into the air from decorative fountains, you were witnessing hydraulic pressure generated by a siphon crossing a valley 2 miles away. But water flow and pressure were just sources of power and convenience. In the next revelation, I'll show you the secret of how Romans kept their water pure enough to drink, a technology so advanced it wouldn't be rediscovered for 1,700 years. What if I told you that Romans understood biological water purification and used techniques that modern water treatment plants only reinvented in the 20th century? The challenge was this: water running 40 miles through channels would accumulate sediment, algae, bacteria, and pollutants. Wells and cisterns in other ancient cities often became breeding grounds for disease. Yet Roman water, when tested by modern archaeologists in still functioning ancient channels, is cleaner than the municipal water in many modern cities. How? The answer lies in a system called the piscina, though its function went far beyond the swimming pools the word later came to mean. At intervals along every aqueduct, typically every few miles, the channel opened into a large settling basin. Here the engineering became almost biological in its sophistication. The piscinae weren't just empty tanks. Each was carefully designed with a specific depth, width, and flow pattern. Water entered at one end through submerged inlets and exited at the other end through outlets positioned at a precise height. As water flowed through the basin, its velocity dropped dramatically. This caused suspended sediment to settle to the bottom. But here's the clever part. The bottom of each piscina was shaped like a funnel, with a drainage channel at the lowest point. A worker could open a valve and flush accumulated sediment without interrupting water flow to the city. The basin runs clear again. A maintenance worker might call to his supervisor, closing the drain valve. We took out 3 cartloads of silt, but sedimentation was just the first layer of purification. The Romans discovered that keeping water in sunlight for several hours killed most waterborne diseases. The piscinae were open to the sky, and their size was calculated to provide a residence time of 6 to 12 hours for the water passing through. Ultraviolet radiation from sunlight disrupted bacterial growth. The Romans didn't know about UV radiation or bacteria, but they observed that water, which sat in the sun, tasted better and caused less sickness. They went even further. Many piscinae had plantings along the edges, specific species of marsh plants that absorbed heavy metals and toxins from the water. The roots created a biological filter. Modern analysis of these basins shows accumulation of lead, copper, and other metals in the root systems of plants that grew there 2 millennia ago. The plants were doing what modern wetland filtration systems do: biological remediation of pollutants. The most sophisticated piscinae had multiple chambers. Water would flow through a series of 3 or 4 connected basins, each removing different sizes of particles, each providing more time for sunlight exposure, each with different plants performing different filtration roles. The final chamber before water re-entered the aqueduct channel was called the Piscina Limaria, the cleaning pool, and it had one more feature that seems almost modern in its sophistication. Romans knew that the clearest water was at the middle depths of a pool. Surface water had floating debris and oils. Bottom water had settled sediment. So the outlet from the Piscina Limaria drew water from 18 inches below the surface through a floating intake that automatically adjusted to maintain that depth as water levels varied. This ensured that only the clearest water continued to the city. Different aqueducts had different purification needs. The Aqua Virgo, which drew from springs, needed minimal treatment, only a few piscinae for basic settling. The Aqua Anio Novus, which drew from a river, had massive piscinae every mile, some large enough to be small lakes. The Aqua Marcia, famous for having the coldest and sweetest water in Rome, had a series of 7 connected piscinae that together provided nearly a full day of residence time and purification. These systems weren't just functional, they were measures of civic pride. The quality of water defined the status of different aqueducts. Wealthy Romans would pay premium prices for houses connected to the Aqua Marcia, specifically because of its superior purification system. This water comes from the Marcia, a property seller might boast. 7 piscinae and 44 miles from source. You won't find purer water in Rome. It was the piscinae that allowed Rome to avoid the waterborne disease epidemics that plagued other ancient cities, that made Roman water safe enough to drink directly from public fountains, that turned water delivery from a basic service into a source of civic pride. Another indispensable element was the system of distribution once water reached the city itself. Water arriving at Rome entered a massive structure called the Castellum Divisorium, the division castle. These weren't simple tanks, but sophisticated hydraulic computers made of stone and bronze. The Castellum of the Aqua Claudia, partially preserved, shows the complexity. A circular basin 40 feet in diameter, with bronze gates controlling flow into 9 separate channels. Each channel served a different priority level. 3 channels fed the imperial palace and critical government buildings. These could never be closed. 3 channels fed the public bathhouses and fountains. These could be restricted during drought, but not fully shut. 3 channels fed private homes and businesses. These were the first to be cut if water became scarce. The genius was in the mechanism itself. The gates weren't manually adjusted. That would require constant supervision and create opportunities for corruption. Instead, they used a weighted float system. As water level in the main basin dropped, bronze floats descended, automatically closing the lower priority gates through a series of linkages. The system was self-regulating, implementing water restrictions without human intervention. A maintenance inspector might check the mechanism and report, "The floats are reading true. Private service at 60%, public service at 90%, imperial service at full." Yours from the Castellum, water flowed through a network of pipes that would make modern cities envious. The Romans used 3 types of pipe, each for specific purposes. Lead pipes, fistulae, for underground distribution and for areas where flexibility was needed. Lead could be bent, joined easily, and resisted corrosion. Ceramic pipes, tubuli, for above-ground distribution and for areas where lead might be unsafe. And stone pressure pipes, tubuli lapidae, for high-pressure applications where even thick lead might burst. The pipe network wasn't random. Romans invented the modular pipe system, with 9 standard diameters called quinaria, based on the Roman inch. A 20 quinaria pipe was precisely 20 times the capacity of a 1 quinaria pipe. This allowed engineers to calculate flow rates precisely and ensured that pipes from different contractors would connect properly. Every pipe was stamped with the contractor's name, the diameter, and the year of manufacture. When archaeologists excavate Roman pipe networks, they can trace the expansion of the water system year by year through these stamps. For private homes, connection to the water system required a license and a fixed fee based on pipe diameter. A homeowner couldn't simply tap into the main with whatever pipe they wanted. An official called the Aquarius would install a calibrated bronze fitting called a calyx, a short section of pipe with a precisely measured diameter that determined maximum water flow. This fitting was sealed with the Aquarius's stamp. "You have paid for a 5 quinaria calyx," the Aquarius might explain. "This bronze fitting ensures you receive no more than your allocation. Any tampering with the seal is a capital crime." The system was so effective that Rome's per capita water consumption was higher than most modern cities, about 300 gallons per person per day compared to about 150 gallons in modern New York City. This wasn't waste. It was the foundation of Roman public health. Constant water flow through the fountains, the baths, the public latrines, the street gutters. It all served to keep the city extraordinarily clean by ancient standards. Now I need to tell you about something Romans drank every day, something that sustained their empire and that we've completely misunderstood. What if I told you that ancient Rome ran on a beverage so important that soldiers received it as part of their rations, workers demanded it as payment, and some of the wealthiest Romans spent fortunes perfecting its creation? Water wasn't just for washing and drinking. The Romans transformed it into posca, a drink that was part of every Roman's daily life, from the poorest slave to the wealthiest senator, though the quality varied dramatically. Basic posca was simple: water mixed with sour wine or wine vinegar, sometimes with added salt and herbs. A legionnaire on the march might mix his ration by saying to his tent mate, 3 parts water, 1 part acetum, a pinch of salt. Keeps the belly sound and the thirst at bay. The acetum, sour wine or vinegar, had antibacterial properties that made questionable water safer to drink. It replaced electrolytes lost through sweat during hard labor or military campaigns. It was more stimulating than plain water but didn't intoxicate like regular wine. But the posca of the wealthy was a completely different creation. The finest versions began with the best wine vinegar, aged in amphoras for specific periods to develop complex flavors. This was then blended with pure water from a specific aqueduct. The aqua marcia was preferred, and infused with carefully selected herbs. Coriander, fennel, mint, rose petals, even crushed pearls for the most extravagant versions. A wealthy Roman hosting guests might instruct his cup-bearer, "Prepare the posca from my private reserve, the 20-year Falernian acetum with rose and honey. 3 parts marcia water, chilled in the snow room." Yacht. The difference between common posca and luxury posca was similar to the difference between mass-market soda and a craft cocktail. Both use the same basic ingredients: water, acid, flavoring, but the quality of ingredients and the care and preparation created entirely different experiences. In the army, posca was essential. Soldiers in hot climates could drink it all day without becoming dehydrated the way they would from wine or beer. During sieges, when fresh water was scarce, Mixing whatever water they found with vinegar made it safer. The famous story of the Roman soldier offering Pascha to Jesus on the cross wasn't an insult. It was sharing his own drink, the beverage that sustained Rome's legions across the world. Pascha was indispensable because it solved the fundamental problem of safe hydration in an age without refrigeration or water treatment plants, while remaining cheap enough for universal access, yet sophisticated enough for aristocratic tables. Even with Rome's sophisticated water system and their ingenious Pascha, there were moments when everything failed. I need to tell you about the winter of 97 CE, when Rome learned exactly how fragile civilization could be. A massive earthquake struck the Apennine Mountains, the source region for several of Rome's aqueducts. Then, before repair crews could respond, an unprecedented winter storm brought freezing temperatures that lasted for weeks, temperatures Italy hadn't seen in living memory and wouldn't see again for centuries. The underground channels didn't freeze. They were protected by Earth's insulation. But the above-ground sections, the bridges and siphons exposed to air, became solid ice. The massive siphon of the Aqua Claudia, with its lead pipes carrying water across a valley, became a sculpture of ice weighing thousands of tons. When ice expands, it tears metal and cracks stone. Workers watching the Claudia siphon heard sounds like thunder as the frozen water expanded and split the pipes apart. Within 3 days, 6 of Rome's 11 aqueducts stopped flowing. The city lost 60% of its water supply. What happened next revealed the true fragility beneath Rome's engineering prowess. Public fountains ran dry. The great bathhouses closed. But the real crisis was in sanitation. Without flowing water to flush the public latrines and wash the streets, waste accumulated. Disease began to spread. Romans who had lived their entire lives with abundant clean water suddenly faced the same conditions as any other ancient city. Desperate measures became necessary. The city's administrators ordered the opening of emergency cisterns that hadn't been used in decades. The water that came out was brown and stinking. A city official examining the cistern might order grimly, "Boil it 3 times before distribution, and pray to Jupiter it doesn't kill them." Romans dug wells inside the city for the first time in generations, tapping into the groundwater they had proudly abandoned when the aqueducts arrived. But the aquifers beneath Rome were contaminated by centuries of occupation. The well water tasted of minerals and worse. People drank it because the alternative was death by dehydration, but dysentery swept through neighborhoods. The wealthy sent servants to the Tiber River with instructions to collect water from specific locations upstream of the city's sewage outlets. These servants would mark their collection spots jealously, sometimes fighting with other household servants over access to the clearest water. The river water had to be settled in jars for hours, then carefully poured off, then boiled. The process consumed enormous amounts of firewood. A wealthy matron might instruct her household slaves, "Use the Tiber water for cooking and washing only. For drinking, we will continue to ration the stored rainwater from our impluvium, 1 cup per family member per day." The poorest Romans, who couldn't afford firewood for boiling or household slaves for collection, drank whatever they could get. Mortality rates spiked. Some desperate families collected snow from the streets, melting it for water, without understanding that urban snow contained the concentrated filth of the city. This crisis lasted for 6 weeks before the weather broke, and emergency repairs could restore basic water flow. In that time, an estimated 15,000 Romans died, not from the cold, not from the earthquake, but from the loss of the water system that had made their city possible. The fragility beneath Roman engineering wasn't in the structures themselves, but in how completely the city had come to depend on them. Rome had optimized for abundance and had lost the old survival skills. It was a harsh lesson. Those who survived weren't the wealthiest with their private stored water reserves, but the wisest, the ones who remembered or quickly relearned the ancient skills of finding, testing, and purifying water from natural sources. Roman water engineering wasn't just about arches and aqueducts, impressive as those were. It was about understanding water as a living system that had to be guided, purified, protected, and respected at every stage from mountain spring to city fountain. The underground channels that protected water from contamination and attack, the inverted siphons that used pressure instead of height, the sophisticated piscinae that purified through settling and sunlight and biological filtration, the distribution castella that automatically prioritized supply during shortage, the modular pipe systems that ensured fair allocation. All of these worked together as a unified philosophy of water management. The unifying principle was this: the Romans didn't try to dominate water through brute force. They studied its behavior, understood its properties, and designed systems that worked with water's nature rather than against it. Modern water systems pump water uphill using enormous amounts of energy. Romans let gravity do the work and used pressure as a tool, not a problem to be overcome. Modern treatment plants use chemical purification. Romans used time, sunlight, and biology. Modern distribution systems rely on constant active management. Roman systems self-regulated through elegant mechanical design. This philosophy came from centuries of hard-won experience. The earliest Roman aqueducts were simple channels that failed frequently. Each failure taught a lesson. Each lesson was incorporated into the next design. By the time Rome built the Aqua Claudia in the 1st century CE, they had perfected an art that wouldn't be matched until the Industrial Revolution gave us materials and energy sources they never dreamed of. The legacy is still visible. Parts of the Aqua Virgo still flow in modern Rome, delivering water to the Trevi fountain exactly as they did 2,000 years ago. When you toss a coin into that fountain, you're witnessing Roman hydraulic engineering that has outlasted empires, religions, languages, and civilizations. The water flowing over those Baroque sculptures follows the same path through the same channels that Romans built before Christianity existed. What other aspects of Roman engineering would you like us to explore? Perhaps their road-building techniques that created highways still in use today, their concrete formulations that grow stronger with time rather than weaker, or their architectural innovations that allowed them to build domes that wouldn't be matched for 14 centuries. Suggest topics for future videos in the comments. The technologies we've uncovered today, the self-diagnosing underground channels, the automatic pressure regulation, the biological water purification, weren't rediscovered by accident. They were lost because we stopped asking how the ancients achieved what they did and started assuming our modern methods were automatically superior. There are more engineering secrets buried in the ruins of Rome, waiting for us to dig deeper and question our assumptions. Subscribe to our channel so you don't miss our next journey into the forgotten wisdom that might reshape how we think about our own technology. Every week, we uncover another piece of knowledge that forces us to reconsider the story of human progress.